Okay, so hello everyone. I am NPI and I will be the host for today's Astrophysics revision session. Um, or the plan of the way I was planning on going for this revision session is I will leave this PowerPoint for you to check out later. I will go over it now just in case you have any questions. But it's mostly this is a really theoretical topic, so there's a lot of questions they asked about like what is definition. So there's a lot of theoretical work and there's basically a lot you have to memorize, which makes it either really easy or really hard. Um, but there's a lot of understanding as well, which I will do my best to explain. So anyway, I will get started with the definitions. So definitions here are some. So a planetary system, which is a set of masses that orbit a star. The solar system, which, as you probably all know, is the planetary system formed by the sun and all the objects that orbit it. It's an important distinction. It's important to learn to the difference between the solar system and the planetary system. Well, the solar system is a planetary system, but not all planetary systems are solar systems. Asteroid is a rocky metallic object which is up to 1,000 kilometers in diameter, and they orbit a star. They are too small to be considered planets, and their small mass prevents them from having spherical shapes. In the case of the solar system, they are mainly in the asteroid belt and in the Kuiper belt. Comets are relatively small masses made of rock and ice that orbit the sun in an elliptical orbit. When they go close to the sun, a tail of dust and gas is generated pointing away from the sun. So as you can see, well, this is a really shitty quality image. It did look better when it was smaller, but so the comet kind of has this huge elliptical orbit, and they have huge periods. Some of them, I mean, the ones that have shorter periods are around 80 years, Halley's Comet, and then there's some that have a period of 200, and even more. And so here you can see that as they get close, they always have that tail pointing away from the sun. That's the solar wind causing that tail. Um, and this right here, the point closest to the sun is the perihelion, and this right here is the aphelion. I'm almost positive. Um, but I will add that to the presentation when I release it, because I'm going off memory right now. Dwarf planet. Um, it's a planet that whose mass is enough for it to have spherical shape. There's this thing that you don't learn in IB called hydrospheric pressure, I think. Um, and basically it depends on the mass and the density, and it is what makes it so that planets collapse under, well, not collapse under their own weight, that's a different thing, but it is what makes it so that they have spherical shape. These planets, they orbit a star, obviously, and they aren't a satellite to another celestial body. So, for instance, the moon is not a dwarf planet, even though it could be bigger than some dwarf planets. It does have enough mass to be spherical, um, and it hasn't cleaned its vicinity of similar-sized objects, which is an important distinction to make from other from planets, as you'll see, because planets have enough mass to have spherical shape. They do orbit a star as well, and they have cleared their vicinity of other objects. So, for instance, if you look at dwarf planets um, in the solar system, you have things like Pluto, which originally used to be a planet, but isn't anymore. Um, and they reclassified it as a dwarf planet because they realized that its vicinity it didn't match this it didn't match this criteria right here. It hadn't cleaned its vicinity of similar sized objects. It was in the middle of the Kuiper belt. Um, so um, a star is a luminous sphere made of plasma that maintains its shape thanks to gravity. I will explain stars a bit more in detail later, but just keep this in mind. Um, and um, and nebulas are an interstellar cloud of dust, hydrogen, helium, and other ionized gases, which are called interstellar matter. And they take a long time to form because they are basically only form due to the gravitational interaction between really small atoms, and they are the main site of star formation. Well, actually, I believe the main and only site of star formations. So a constellation is a bidimensional pattern of visible stars. The stars in the constellation don't necessarily have anything have anything in common. Um, and it's important to learn learn the difference between star cluster and constellation. A constellation is a pattern in the night sky, and I'm gonna air quote pattern because it's a lot to do with imagination. But those stars that they don't necessarily have to have anything in common. Whereas in a star cluster, which are stars that are actually gravitationally attracted to each other, that are close, well, quote unquote, close to each other in space. There are two types. You have globular clusters, which are older, like these stars are older. There's roughly 10 to the 5 stars in them, and they have an approximate diameter of 10 to the 14 kilometers. Open clusters, on the other hand, they have younger stars, 10 to the 3 stars in them, so they have a smaller number of stars, but roughly the same diameter, which means they have a lower density. And this causes that in time they can disperse due to other forces in the system, while globular clusters tend to stay the same for basically throughout the lifetimes. And something I would like to add to that is clusters are usually a consequence of a nebula um, creating several stars. Just as well, a nebula creates stars, and those stars are obviously together because they were formed in the same place. Mm, Galaxy, it's a set of thousands upon thousands of stars that group up in orbit around a common center of mass. Our galaxy is the Milky Way, as you probably all know, and it has a diameter of 100,000 light years. The center of mass in it is usually, I believe, a black hole. It is definitely a black hole in spiral galaxies, but I'm not entirely sure if elliptical and lenticular galaxies have a black hole in the middle. I'm pretty sure they do, but they're not going to ask you in the exam, so you don't need to know that. A galaxy cluster is a group of galaxies that are bound together by gravity. Our cluster is called a local cluster, and uh, and the supercluster is a group of it's a group of actually this is wrong. It's supposed to be clusters. It's a group of clusters bound together by gravity, and they are believed to be the greatest structure in the universe. As in, superclusters don't group up to form megaclusters or some stuff like that. Observable universe. It's the part of the universe that we can observe. So the one we can see, since the speed of light is limited, not all the light reaches us from everywhere, and it has a diameter of 9 times 10 to the 10 light years. You don't need to know this, but you do need to know what the observable universe is. So units, since the distances in Astro are really, really big, we mainly use 3 units. You have the astronomical unit, which is the average distance from the Earth to the Sun, which is not constant throughout the year. The orbit is roughly slightly elliptical, as given by Kepler's law. Light year, it's the distance covered by light in a year, which has this quantity right here. You can actually compute it yourself, just knowing the speed of light and multiplying by just calculating how much it travels in a year. So if it travels 3 times 10 to the 8 meters a second, then just multiply that by the numbers of seconds in a year, and you've got this quantity right here. The comma is supposed to be a decimal point, but I'm Spanish, so I actually just did a comma instead. A parsec is a distance to a star that has a parallax angle of 1 arcsecond. And we will look at this in a second, what this means, what a parallax angle of 1 arcsecond means. Distances are usually actually written in megaparsecs, because they are so huge that not even that, which is an enormous distance if you think about it. I mean, the radius of the Earth is 6,000 kilometers, and I mean, it's just, yeah, they're really, like, we're talking huge orders of magnitude, and even then, they don't even get close to the scale, to the cosmic scale. So, parallax method. It's a method to measure the distance to close stars, 100 parsecs from Earth and 1,000 parsecs from a space telescope. Can anyone tell me why there's a difference between how long we can measure, why we can measure more distance from a space telescope than from Earth? Hmm. Yes, indeed. It is because of the atmosphere. There's the light from the stars kind of bounces off in the on the particles in the atmosphere, and it's called I think it's called atmospherical distortion, and this basically causes the um, ground telescopes to not be able to measure distances as great as space telescopes. There is something called adaptive optics, which kind of compensates, but it's better to just use a space telescope for measuring distances to stars, especially when you're looking at short wavelengths. Um, so it's the visual effect by which a close object appears to change positions with respect to objects further behind it when observed from different positions. So you may have done it in class, but if you stick your finger out with respect to your screen and kind of close one eye and then close the other eye, you might see how the finger appears to move with respect to the background. Um, this is basically the same principle that parallax uses to measure distances to stars. And it consists in measuring the parallax angle and using this formula right here, which is distance in parsecs is 1 divided by the angle in arcseconds. So here's the diagram. So essentially you take two measurements 6 months apart from each other. And as you can see, this would be the projection of the star from here, and this would be the projection of the star from here. So you can kind of draw two lines, and where they intersect is the actual position of the star. So the measurements are taken 6 months apart so that a triangle is formed, so that you can apply trigonometry, and the months in which they're taken depend on the star. And the angle is measured in arcseconds because the variation is really small, and they're always taken with respect to stationary background. So luminosity and apparent brightness, this is about stars. So apparent brightness is the intensity, which is the power divided by the area, received on Earth. It's measured in watts per meter squared. And yeah, the apparent brightness of the sun is 1,360 watts per meter squared. And the rest of the stars have around 10 to the minus 12 watts per meter squared, which means they're really dim, and that's why you can see them throughout the day. Luminosity is the total power radiated by a star in the shape of electromagnetic waves. It's measured in watts, and the luminosity of the sun is given by this. You can compute it easily. It's just using Stefan's law right here. So the apparent brightness is this. So it's brightness equals luminosity divided by 4 pi d squared. If you want me to, I can actually go over how you get this formula. But if you know where it comes from, I will just skip that. It's a pretty straightforward concept if you think about it. It basically just has to do with the light spreads out in a sphere, and so you have luminosity divided by the size of that imaginary sphere, so you get watts per meter squared, or per unit area rather. And so at a star, it behaves a lot like a black body. It is basically a black body, and so we can define its power as a function of its temperature using Stefan's law right here. This is Stefan Boltzmann's constant, which is in the formula booklet. I believe it has a value of 5.83 times 10 to the minus 13, but I'm not sure. This is the area of a sphere, which is 4 pi r squared, and T squared is the temperature, T to the fourth. So basically what it's trying to say is that luminosity, the higher the radius and the higher the temperature, the more luminous the star will be. Stellar characteristics and stellar evolution. So a star basically, how it works, it fuses elements in its nucleus, radiating energy outwards, and that counteracts the pressure exerted by gravity, which basically kind of makes it balanced. Well, I'll explain that a bit more in a bit. So essentially, so the outwards pressure, the outwards force exerted by fusion counteracts the gravity inwards and prevents the star from collapsing. But not all stars are in equilibrium, which is when the outwards energy resulting from fusion balances with the inwards force exerted by gravity. And that makes stars have a constant volume. This is a characteristic of main sequence stars. Main sequence stars are in equilibrium. Other stars are not. Binary systems. Stars can be alone or with another star forming a binary system. By the way, if I'm going too fast or you don't understand something, just unmute your mic and or type it in chat and tell me. I will be more than glad to stop and make an explanation. So stars can be, well, they've binary systems. There's also ternary systems and quaternary systems, and there may even be more. But anyway, binary systems is what you need to know. So you have visual binaries, which are two distinct stars that can be seen with a telescope. spectroscopic binaries, which is when analyzing the spectra from the star, one can see that the wavelengths at a given point split up, which is essentially this. So you're looking at the spectra, and then you see that there is suddenly like two different wavelengths. And this is because one of the stars is moving towards Earth, so it's being blue shifted, while the other star is moving away and it's being red shifted. So there's a variation in wavelength. And then you have eclipsing binaries, which is when analyzing the brightness of a star, one can see dips due to their star getting in front. So you will have, this is the brightness of the combined stars, then one star gets in front of the other with respect to the plane of the Earth, and that causes a dip in the star's brightness, since well, part of the other stars is being blocked. And yeah, this is also a method that is used to identify planets and planetary orbits. It's called primary transit, and it basically consists of the same thing. You look at the brightness of a star, and suddenly if you see a dip, that means a planet got in front of it and blocked part of its starlight. And there you go. Boom, you found a planet. There are other ways to find them as well, but that's just one of the most traditional ones. Okay, so depending on its characteristic, a star can fall into one of the following spectral classes. I'm not going to read out this out loud. You can read it yourself. But essentially, these are the spectral classes. Main sequence stars, by the way, not white dwarfs, not supergiants, and their color. There's mnemonics for this. I didn't write anything here, but you can. I personally use only bat astronomers forget generally known mnemonics. Other people use "Oh, be a fine girl, kiss me," which also has an extension for white dwarfs that I don't remember. So stellar evolution. How are stars born? Well, a star is born when the nebula that it comes from meets the Jeans criterion. This is the Jeans mass, and this is the formula. There were several formulas for this. This is just the one I found in the IB book, so it is the one I'll be sticking to. I don't think you need to have it memorized. But anyway, so if the mass of the nebula is greater than the Jeans mass, the nebula collapses and forms stars. And well, therefore, you can probably see from here that the nebula has more probabilities of collapsing if it's smaller, which means it has a higher density, and therefore this factor is bigger. This term is smaller, and the whole thing is smaller. It has low temperature, so this is smaller, and this whole thing becomes smaller. Or it has a very high mass, which this is greater, and this whole thing becomes smaller. A protostar is the period of evolution starting when a star is a cloud of matter until it reaches the main sequence. So it's important to note that a protostar is not a kind of star, it's a process. So any star that is being formed until it reaches the main sequence is called a protostar. Main sequence. So this is like the main life of the star. Our sun is in the main sequence. Most stars are in the main sequence, as we'll see in a second. So a star is in the main sequence when in its interior, so in its nucleus, hydrogen atoms are being fused. And stars in the main sequence are always at equilibrium. So the outward force, the outward energy liberated by fusion counteracts the gravitational pressure inwards, and the star doesn't has a constant volume. The mass luminosity relation, you can due to having stronger gravitational forces, they're more massive. The more massive stars have hotter nuclei, and therefore need a faster speed of fusion to counteract their collapse, right? And so this leads to them being more luminous, since they need to burn more fuel to keep to counteract their inwards pressure. They basically become more luminous, and this is the relation. There is not a factor of proportionality, I believe. Usually, I think you can just approximate it. You can just do L is approximately mass times mass to the 3.5. So more massive stars spend less times in the main sequence, which basically, for the same reason they are more luminous, they need to burn more fuel to counteract the pressure exerted by gravity. And this is the relation. It's empirical, meaning it's gathered from experimental data. This is not a derived relation. So it's just roughly experimental. We've just seen the data and we've said, okay, this sort of fits it, and we called it a day. And the sun will be the main sequence for roughly 10 to the 10 years. It's been there for a while. So it's not going to be there for 10 to the 10 years more. But don't you worry, it's still got like 5 billion, I think, years left in the main sequence. So you won't be here. You won't be around by the time it turns into white dwarf or into red supergiant. And it will change into a red giant first, but you won't be there anyway. So fusion processes in the main sequence, I believe this is high level, and I'm not entirely sure even if it's high level. But in the nucleus of a star, mainly two processes occur, right? So what it fuses, it depends on the mass of the star. You have the PP cycle, which is the proton-proton cycle, which has three phases. So two protons create a deuterium and release a positron and a neutrino, and then the deuterium fuses with hydrogen with a proton. By the way, a proton is what astrophysicists call hydrogen atoms. Anything that isn't helium is also called a metal. So that's just how they roll. So if you hear the word metal and me say the word metal, sometimes I'm not talking about actual metals. I'm talking about anything that isn't helium. So it forms a helium and a photon, which is basically the helium is excited and it gets de-excited. Two helium-3 atoms combine to form helium and two hydrogen atoms, and then the process starts again. And it is predominant in the nucleus. It is predominant in stars with a temperature in the nucleus lower than 2 times 10 to the 7 Kelvin, which is, for example, our sun. Our sun basically creates, well, yeah, it creates all of its fuel from burning, from the proton-proton cycle. Then the CNO cycle, I'm going to go over it quickly. This one is more, it's longer. So it has 6 phases. A proton combines with a carbon-12 atom to form a nitrogen-13 and an excited nitrogen-13, which then excites itself by emitting a neutron, photon, I mean. Then the nitrogen-13 goes to the carbon-13, releases a positron and a neutrino. And I mean, I'm not going to read over it. You can see the reactions here. If you have any questions, read over it and stop me. So it occurs only on stars with temperature in the nucleus greater than 2 times 10 to the 7, where it is predominant. Okay, outside the main sequence. So once the star leaves the main sequence, there are several things it can do. I did list, these are the ones you learn in IB, there can be a ton more. I don't know all of them, to be completely honest, but so it can become a Cepheid variable, which is a type of star whose outer layers expand and contract periodically. We will be doing an exercise about this later. It's a standard candle. So a standard candle is an astronomical object. By the way, this is just what a standard candle is. This is not something that I start leaving the main sequence maybe called. It's an astronomical object of known luminosity, which makes it possible to determine their distance to Earth using their apparent brightness. They're really useful. So if you know their luminosity, you can measure their apparent brightness on the surface, and just using the formula for apparent brightness, which is B is equal to L over 4 pi d squared. If you know L and B, you can solve for D, and then you can roughly know the distance to that part of the universe. Red giants are stars with a mass lower than 8 solar masses that have left the main sequence. Their size increases considerably, making their surface temperature decrease. And our sun, for example, is going to become a red giant. And red supergiants are like red giants, but bigger, and they have a mass greater than 8 solar masses. For those of you who are thinking about hypergiants, those of you who are a bit more who've looked at this maybe outside, do just note that hypergiants are not an actual formal thing. They are a kind of distinction, but they are completely formalized. So when fusion ends in the nucleus, one of 3 things can happen. It can either become a white dwarf, it can become a neutron star, or it can become a black hole. White dwarfs are red giants, which eject their outermost layers in a planetary nebula. If any of you want to stick around later, I do have a simulator that I can use to simulate this stuff, but I won't do this in the recording because it's going to take forever. So the remaining nucleus, the remnant, is called a white dwarf. Electron degeneracy pressure is basically what prevents the star from collapsing, right? So when the star when a red giant finishes its life cycle, um, it starts collapsing onto itself since it doesn't have any more energy to prevent itself from collapsing, and it starts collapsing under its own weight. This causes electrons in the orbitals to get excited to other energy levels due to Pauli exclusion principle. So the lower energy levels get filled up, and the electrons are forced to higher energy level due to Pauli exclusion principle, and this creates a pressure that prevents the star from collapsing further. The Chandrasekhar limit is the maximum mass that the remnant nucleus can have in order to become a white dwarf. It is, I didn't write it here, but it's 1.4 solar masses. And unlike the Oppenheimer-Volkoff limit, which we'll see in a second, it does have a defined exact value. So if you're higher than 1.4 solar masses, you will not become a white dwarf. A red supergiant, so a neutron star is when a red supergiant goes kaboom. And if the remaining nucleus has a mass between 1.4 and 3 solar masses, then it becomes a neutron star. So neutron degeneracy pressure, right? It's the same concept as the electron degeneracy pressure. So the I should actually so the neutrons, the electrons, due to a process called key capture, fuse with protons and create neutrons. And then everything is a neutron. So, and those neutrons, since they're fermions, they're subject to Pauli's exclusion principle, and they get excited. And so the lower levels fill up. The neutrons are forced to higher energy levels, and this causes again a pressure, which is greater than the electron degeneracy pressure that prevents the star from further collapsing. These are one of the densest things in the universe. I would say the densest, but that title goes to black holes. But if you don't go black holes, neutron stars are the densest thing in the universe. Oppenheimer-Volkoff limit is the upper mass limit of a neutron star, which is not defined to a certain value, as it can be. It is somewhere between 2 and 3 solar masses. And when I say this, I don't mean that it's 2.5 or 2.6 that we don't exactly know. It's that it's just not doesn't have a certain value. It changes from it changes depending on the star. So a black hole, you probably all know what black holes are. So it's a star that that leaves a nucleus greater than 3 solar masses. It will form a black hole because the neutron degeneration pressure is not enough to stop the collapse, and the star keeps collapsing further and further and further until it collapses into a single point called a singularity, which has infinite density, but a certain mass, to be completely honest. And this this creates a black hole. This is more a relativity topic, and I wanted to cover the relativity as well, but it has some parts that I haven't covered in university. So, but yes. Mm, yes, neutron stars are more denser than white dwarfs. Yes, they think about it this way. Um, So when you have a white dwarf, you have a star of a certain mass. I think it has to be lower than 8 solar masses. I don't quote me on that, but I'm pretty sure somewhere around that range. And that mass collapses into but it's the mass of the nucleus is around 1.4 solar masses at most, whereas a white dwarf has more mass but roughly the same volume. Roughly, they do change in volume, but yes, neutron stars are way denser than white dwarfs. White dwarfs are really dense as well. Something I would also like to add now that we're on the topic. White dwarfs and neutron stars do not have fusion going on their course. All their light is actually kind of dimming. So white dwarfs actually kind of turn off, sort of like a light bulb. Eventually, like they're not producing energy. Is what I'm trying to say. Uh, yeah. So they're kind of like a light bulb that you just leave turned on. It will eventually turn off. They just have a ton of heat and a ton of energy, but that energy eventually just radiated outwards, and they don't have an in-house source of energy to make up for that. Okay, so types of supernova. There are a lot of types of supernova. But okay, so a supernova is a very sudden, luminous, and unpredictable stellar explosion. It constitutes the death of a star. Here we will be looking at 2 types. There are more. There's type 1a, type 1b, type 1c, type 2, type 3, I think. But anyway, here we'll be looking at type 1a and type 2. I would also, some of you may have heard about Beta Hoyser going supernova. And because it's unpredictable. When I say unpredictable is that we can't really know when it happens, but we have an idea of when it's near. As in, we can't say, oh, it's going to happen this exact moment. But we can sort of say, okay, it's about to happen because we know when a star kind of has burnt most of its fuel. So type 1A supernova on this diagram is not supposed to look like this. This looks like something you would find on a Hawaiian t-shirt. It's supposed to be an actual diagram of luminosity in type 1A supernovas. But in a binary system, where one of the stars is a white dwarf, the gravitational field of the white dwarf can be large enough to attract mass from its neighbor. And they are used as a standard candle since they always have the same luminosity. Can anyone tell me why they will always have the same luminosity? No? No one? Okay, hold on. Then, so,
because of the same mass.
hmm?
Same mass.
Yes. So essentially, it has something to do with that. So it's a white dwarf, which means its maximum mass is the Chandrasekhar limit, right? It cannot have a mass greater than 1.4 solar masses. And as we saw before, the mass is proportional to the luminosity. Therefore, since the white dwarf can only grow to 1.4 solar masses, whenever it reaches those 1.4 solar masses, it is going to become a neutron, and it's going to have that peak that same luminosity when it does. When it becomes a neutron is when the type 1a supernova happens. And so it becomes a neutron star, bad. I did say neutron 3 times, didn't I? Well, anyway, it becomes a neutron star when it reaches those 1.4 solar masses because it's been absorbing mass from its neighboring star. So it will reach the Chandrasekhar limit. It will become a neutron star. It will undergo a type 1a supernova. But since it always has the same mass when this happens, because it is always becoming a neutron at 1.4 solar masses, we will always get the same luminosity. And that's why they use the standard candles. We know the luminosity it will have because we know the mass it will have. And I actually want to show a diagram of this, but apparently, apparently it didn't work. So I'm just going to look one up in Google. But let me see if I find the diagram that I'm looking for. Okay, yeah, here. So as you can see, right, if you plot the luminosity, you can see that it always peaks at the same spot. And this is what we use to find the well, yeah, this is how we know that they always have the same luminosity, and therefore, again, by measuring their apparent brightness, we can actually tell the distance to the star. So, okay, so next we have the type 2 supernovas, which are a red supergiant collapses under its own weight. So essentially, what happens is when a star is cannot burn anymore. When a star cannot burn anything more, use anything more, it cannot release any energy. It cannot prevent gravity from becoming predominant and kind of making the star collapse under its own weight. So then the star kind of collapses and it releases a ton of energy in all directions, and this destroys the outer layers of the stars and propagates really long distances. They're really luminous. As in, for example, there was no supernova, type 2 supernova for close star. I mean, they have to be close because, but for example, and by close I mean it was. I don't mean close as in it was Alpha Centauri, which is 4 light years away, and then I mean like several megaparsecs. But this star was actually visible in daylight. Yeah. So this star was actually visible in daylight because the explosion was so bright. Betelgeuse will also undergo when it explodes a Type 2 supernova, and we probably won't be around to see it, unfortunately, but it should be visible during daylight. As in, you would see the sun, and then you would see another spot which corresponds to Betelgeuse going supernova, which I find really cool. I really think that's really cool. HO diagrams are a way to represent stars graphically. They relate temperature and luminosity, and it's important to note that temperature decays along the horizontal, as in it doesn't increase as you would usually have an increasing x-axis. You actually have a decreasing x-axis, and the axes tend to be logarithmic, or they are actually always logarithmic because there is great changes between stars. You do need to note roughly the shape of a HO diagram for the exam, so just kind of keep this in mind. As you can see, well, this is just the color. You don't need to know this, but as you can see, the white dwarf, or the temperature, my bad, decreases along the x-axis. I've actually done this experimentally, and I've analyzed data from stars, and you actually get this exact pattern, which is pretty cool. But if you analyze data from a ton of stars, you will actually see that they fall in this exact pattern. So you'll have stars here along the main sequence. You will have some stars here at the bottom that are white dwarfs. You will have giants here, red giants, and supergiants here. And there's some along here as well for like blue supergiants and other kinds of stars. And then for our sun is like around here. It's a G-type star, and it just sits here roughly. And if they ever ask about if they ever ask you to tell them what the sun will do when it leaves the main sequence, it's roughly here right now. It will become a red giant, and it will kind of go to a white dwarf. Um, so it becomes a red giant in roughly 5 billion years, and then once that is done, it will emit a planetary nebula and and become a white dwarf. So hold on, somebody's asking a question, so I'm going to stop the recording and just if you have a question, just you can also mute your mic and ask it if you rather.
Oh, I can ask a question like this.
Yeah, sure. Go ahead.
Yeah, sorry. Can you hear me?
Yeah, I can.
Yeah, so I was doing a paper at the same time, paper 3, and what happens when a main sequence star has a mass larger than the Earth? What kind of
Has it
star evolution will it take?
has a mass larger than what? Excuse me.
The sun.
Oh, okay. It depends on the mass, right? Because I mean, as I said, the sun is roughly somewhere here. So there's a ton of stars that have a mass larger than the sun. But so it depends. So if the mass is greater than, well, it will always become a red giant or a supergiant, depending on its mass. I think if it has a mass greater than 8 solar masses, it becomes a supergiant. Yeah, so if it has a mass greater than eight solar masses, it will become a supergiant, which means it will go up here to the in the Hertzsprung-Russell diagram. Whereas if it doesn't, it will go to the giants part right here. And then after that, depending on it will go supernova at one point, right? So it will stay as a red giant for millions of years, and then at one point it will go supernova, and depending on its mass, so depending on its mass, it will either become a white dwarf, a neutron star, or a black hole. It will become a white dwarf if so after it goes supernova, it will emit a nebula. It will kind of expel all of its outer layers. I actually have a software to simulate that, so I can do that later if you want to stay and see it. But it will kind of get rid of all its outer layers, and there will be a remnant left behind. If that remnant has a mass lower than 1.4 solar masses, it becomes a white dwarf, which is what will happen to our sun. If it has a mass between 1.4 and like 2 or 3 solar masses, it becomes a neutron star. And if that black hole has a mass greater than 3 solar masses, it becomes a black hole. So I think the when it comes to the actual mass of the star is 8 solar masses or less becomes a white dwarf. Between 8 and 40 becomes a neutron star, and 40 or more becomes a black hole. I think that's an extinction, but I always use the remnant since it's more precise. Did that answer your question?
Yes, it did. Thank you so much.
No worries. So okay, stellar spectrum. So by looking at the spectrum of a star, we can measure the following quantities. This is really important. Okay. Hold on, there's more. Okay, so regarding type 1a supernovas, is it formed when a red giant changes into a white dwarf? No. It is formed when a white dwarf changes into a neutron star. So, oh, damn it, I should have made a drawing. Hold on, I'm just gonna, yada, yada, yada. Damn it. Can you draw? Hold on. Okay, so, so you have a system, so at one point you have a so you have a system with two stars, one of which is already a white dwarf. So we part on the assumption that one of the stars, you part of the assumption one of the stars is already a white dwarf. So you have a white dwarf, say here, and I can't write apparently, and then you have a whatever. So you have a white dwarf, kind of like this, and then you have another star, which can be any other star. It can be a red giant. It usually is a red giant or a main sequence star, and they're kind of orbiting each other in a. Actually, this is a horrible drawing. I'm going to give up on drawing. Um, but so you have um, so you have the two stars. One of them is a white dwarf, so it has already emitted its planetary nebula. It has already become a white dwarf. And then at one point, that white dwarf starts collecting mass from its neighbor, increasing its mass until it reaches a Chandrasekhar limit, and it becomes a neutron star. So the Type 1a supernova is what happens when it reaches enough mass. Oh, the drawing is invisible? Okay, it doesn't matter, it was horrible anyway. Um, but, so when it has enough mass, it will continue gathering mass from its neighbor, and then it will surpass the Chandrasekhar limit, become a neutron star, and then the Type 1a supernova will happen. Well, as soon as it reaches the Chandrasekhar limit, it becomes a neutron star, and the Type 1a supernova happens. So no, it isn't. When it doesn't happen when the red giant changes into white dwarf. It happens when the white dwarf changes into a neutron star. Um, well, yes. So there will be at some point a red giant in a binary system, and that red giant will at some point become a white dwarf, and that white dwarf at some point will become a neutron star. That's kind of the sequence of events. Um, yes, exactly. So after it turns into a white dwarf, it doesn't always happen, right? The fact there's a white dwarf in a binary system doesn't mean there will be a Type 1a supernova. Um, but yeah, so essentially, if this gravitational field is strong enough, it will start kind of gathering mass from its neighbor, and it will increase its mass and go supernova at one point when it reaches the Chandrasekhar limit. I can actually simulate it later. If you guys want to stick around, we can play around with simulations. Um, so okay, so looking back to the stellar spectrum, we can measure the following quantities, right? We can measure the wavelength at which the emitted radiation has its peak intensity, which will then let us know the temperature of the star using Wien's law, which you can see written there. The chemical composition, which we can actually see if you guys, well, I mean, you all did topic 7, so you know about the absorption spectra and the emission spectra. If we look at the emission spectra of a star, we can see what wavelengths are missing. And by looking, I should have added an image. By looking at the wavelength, but by looking at the wavelengths that are missing, we can kind of identify the elements that correspond to those wavelengths that have those absorption spectra, and therefore we can see the chemical composition of the star. Is this clear, or would you like me to try to draw it? And then we can also we can also know the speed at which the star moves. And how, you ask? Well, since we know how the emission spectra, absorption spectra of different elements look, we can also know um, if they're shifted. So if we see, the hydrogen, for example, say we see the hydrogen spectrum, and we see the hydrogen absorption lines in a certain spectrum of a certain star, but we see they're shifted. We can attribute that to Doppler shift because the light is moving. And we can say, okay, so since it's Doppler shifted however many wavelengths, we can actually, using Doppler shift, compute its actual speed, the speed of the star at which the star is moving. Is this clear? I can do a drawing, if you'd rather. It will be easier to understand that way, but if you can grasp this just from me explaining it that way. And then Finn's law, it's an empirical law. Is it empirical? Maybe. Yeah, it's empirical. It relates to the maximum wavelength at which a black body can emit radiation, and its temperature. This is really important. I think you do this in topic 8. But it basically states that the maximum wavelength times the temperature is equal to this constant, 2.9 times 10 to the minus 3 meters Kelvin. This is really, really important. They always ask a question regarding this, and it's really straightforward to get. You just solve for lambda, or solve for t, whatever the hell they ask for, and there you go. Boom. I think it's like 2 marks usually. So then we'll be moving on to cosmology, which is not to be confused with astrology. I will punch whoever says that. And this is basically the study of the cosmos. It's personally one of my favorite branches of this subject, but I like astro a lot. Anyway, so we'll start by looking at Hubble's law, which is basically states that the speed at which a galaxy recedes is proportional to its distance. So, as you probably all know, the universe is expanding and everything is moving away from us. Which is kind of depressing but anyway. So everything is moving away from us. Everything is running away. And Hubble said, okay, that's proportional. The velocity at which the galaxy is moving away from us is actually proportional to the distance. So the further away a galaxy is, the faster it's moving away from us. So here in this formula, which is in the formula booklet, is V is the speed of recession, H0 is the Hubble's constant, which actually isn't constant, which is hilarious. Different measurements actually get different values of the Hubble constant, and the other values are not within error bars, and we don't have an explanation for this. So I believe the Planck probe, was it Planck probe? I don't know, maybe it was, got one measurement, then another experiment got another measurement, and when you check the error bars, they don't have anything in common. And then D is the distance in megaparsecs. And note that the units of the Hubble constant are second to the minus 1, not hertz. It's not a frequency. Don't say hertz. But since megaparsecs and kilometers are both units of distance, right? So kilometers, megaparsecs, both units of distance, they cancel out. The value of the Hubble constant is constant in space, but not in time. And what the hell does this mean? Well, it means that right now, throughout the whole universe, the Hubble constant is the same, but a million years from now, it will have a different value throughout the entire universe. So it's not like Planck constant, which will always be the exact same throughout space and time. This is constant in space, so it's the same value now everywhere, but not for all time. It will change in time, and it has changed in time before, as we will see in a second. So if Andromeda is approaching us due to gravitational interaction. So as you saw, as I explained earlier, there's this structures called clusters, superclusters, right? And the Andromeda galaxy, and the Triangulum galaxy, and the Milky Way galaxy, aside with a ton of smaller galaxies, form what is called the local cluster. And these clusters, they're gravitationally attracted to each other. So Andromeda and the Milky Way are actually bound to collapse at some point because of the gravitational interaction. So they are both close enough to each other that they can mutually attract each other gravitationally. It has so this kind of yeah, I mean that's sort of the explanation. It's gravitational interaction. Did that clear it up? Okay, sweet. So expansion of the universe. The universe is expanding. It's expanding faster every time. It's not slowing down, which we'll get to in a second. But there is three evident. Well, three pieces of evidence. There's a ton, but okay, the ones we're going to look at are redshift. The galaxies, as I explained before, are getting away, further away from us, and the cosmic microwave background. We'll commonly refer to CMB. And note that the expansion of the universe is not an expansion from the side. So it's not. No one is grabbing the universe and stretching it. It's rather that there's space being created, and I'm going to quote that, but it's being created into galaxies. I don't really understand this very well myself, but I kind of picture it as a plum cake, which you probably have heard. Some of you may have heard before. So when you put a plum cake and you put raisins in the plum cake and you leave it in the oven, kind of the raisins spread apart, but they spread apart into like in the plum cake. They don't. There's no distance. No one is stretching the plum cake apart. It's sort of like growing from the inside. That's sort of the same concept that happens to the universe. And if you ask me what is the universe expanding into, I really have no clue. I think most people say it's itself, but I have trouble getting to coming to terms with that. So I don't know what the universe is expanding into, but I would say probably itself, which is really weird. So basically, this is a diagram. So this is the universe before, and then you can see how it, little by little, like distance kind of grows. Okay, age of the universe. The age of the universe can be calculated by doing the inverse of the Hubble constant when it has units of inverse time. Which is well, yeah, basically you just compute the Hubble constant in seconds to the -1, and then just do 1 over that. It's important to note that this is only an approximation, and it's greater than the real value, and there's 3 reasons for that. Can anyone tell me what they are?
Is it because the universe isn't expanding at a linear rate, and
That's
Hubble assumed that it
one of the
was?
reasons.
Is it because that? Did you say yes
Yeah,
or?
that's one of the reasons.
Oh, okay, okay.
Okay, well then I'll say the other two. One of the other reasons is that the expansion did not, as you said, one of them is it isn't linear. The other one is the universe isn't expanding at a constant rate. Which means, well, actually, no, yeah, that's the one you said. My bad. The other one is that the expansion of the universe did not start immediately after the Big Bang. Which is so the Big Bang happened, and sometime happened, and then the expansion of the universe started. And there's also the fact that the error or the uncertainty, my bad, in the age of the universe is significant, and the Hubble constant is significant. As I pointed out before, it's huge, so you can't really like it's got a huge error bar, so it's really hard to actually know the age of the universe using this. It's just an approximation. Okay, so cosmic microwave background. Some guys called Penzias and Wilson discovered it's actually a pretty interesting story, but this is not history lesson; it's physics. So they discovered that there was a microwave radiation coming from all directions, and this radiation was not linked to any source, and looked a lot like the radiation coming from a black body at very low temperatures. So basically, that wherever they pointed the telescope, they could see this same radiation. So and that was actually the CMB that won the Nobel Prize in I don't know what year, but it won the Nobel Prize. So what characteristics does it have? Well, it's isotropic, which I will get to in a second. Basically means the same, it's in every direction. It has a temperature of 2.76 Kelvin, so it's really, really cold. And it's found in microwave wavelengths of around 1.1 times 10 to the minus 3, and that's there's supposed to be meters in there, so that's meters. So the wavelength is really long. You can actually compute the wavelength if you know the temperature by using Green's law, by the way. And so the CMB is evidence for the Big Bang. It's actually one of the greatest evidences. So it's the radiation of the universe itself, well, of the beginning of the universe that cooled down to 2.76 Kelvin. Some of you may know this. This is not part of the syllabus, but the universe at the beginning was opaque. Light could not escape. And it took, I think it was, well, a long time. I don't exactly remember the time, but for like 300, I think it was 300 million years, the universe was dark. there was nothing. Light could not escape. It was bouncing back and forth between particles. And then at one point, after the Dark Era, the CMB was created. Well, the CMB was created, it was emitted, and it's been traveling the universe ever since. So it's basically the closest thing we have to the Big Bang, but we can't really see back the Big Bang because there was no light. As bizarre as that sounds, there was no light at the beginning of the universe. It was all opaque. So a time after the Big Bang, radiation started traveling through the universe because at the beginning it couldn't. And due to the expansion of the universe, right, since the universe has been expanding, the wavelength of this radiation has been stretched. So kind of like if you grab the wavelength and pull it, like start pulling it, sort of thing. So it's been stretched, and therefore its wavelength has increased, and accordingly, according to Wien's law, its temperature has decreased. So CMB fluctuations, this is definitely HL, but it's really interesting anyway. So I'm gonna go over it now anyway. Either or. The CMB is not perfectly isotropic, meaning it's not exact same in every direction, and it's not exactly constant. But there are really, really, really small variations called anisotropies that correspond to 0.0002 Kelvin. So they're insanely small. And they're like these red dots that you see and these green dots that you see. They're variations in temperature, and they correspond to variations in density in the universe, which basically tells us when structures were created. So these variation temperature correspond to the creation of galaxies and well, yeah, mainly galaxies because planets and stuff, which is really cool. Cosmic scale factor. So it's used to represent the size of the universe by comparing the distance between two specific points at different moments in time. So the cosmic scale factor, represented by an R at time t, is the separation of the galaxies at that time t, and the separation of those galaxies now. It's dimensionless, it doesn't have any units. As you probably see, both of them are meters or parsecs or whatever you want to use, but they're both units of distance. It changes with time, so, well, yeah, that's pretty self-explanatory. Now, R is equal to 1. Before, R was lower than 1, and in the future, it will be greater than 1. And this applies to whenever you read this. So if you read this a million years from now, R will still be 1. It used to be lower than 1 before, and it will be greater than 1 thereon. Cosmic scale factor and its relation with temperature. So the universe used to be smaller and hotter. As such, we can link the temperature and the wavelength of the cosmic microwave background using Wien's law with the cosmic scale factor using the following formula. So lambda max is proportional to R, which implies that whenever T is proportional to R. I don't think you ever use this actually, but it's good to know. Redshift and blue shift. Okay, so what is redshift and what is blue shift? Redshift is when you're moving away from the source, your wavelength gets longer and you shift to red, since that's a lower wavelength in the visible spectrum. And blue shift is when you're moving towards the source, your wavelength kind of gets compressed, and it tends to blue, which is a shorter wavelength in the spectrum, in the visible spectrum. And there are several causes for blue shift and redshift. Doppler effect. In space, radiation shifts to blue when two galaxies get close, and to red when they move apart. So, for instance, Andromeda, that Noise mentioned before, it's blue shifted because it's moving towards us, right, due to gravitational interactions. But all the other galaxies are red shifted since they're moving away from us, as we explained earlier by Hubble's law. Well, all the other that are in our cluster. And then cosmological redshift, it's the emitted wave expands since the space is expanding. So basically, kind of like the analogy I made earlier, if you can do like kind of stretching it. And there's no such thing as cosmological blue shift. There's nothing just compressing the waves together. And gravitational redshift, you only need to know it exists. You don't need to know what it does. I don't even know what it does myself, to be completely honest. Okay, so formulas. This is actually one thing I forgot to mention. Only works for recessionary speeds of open 25C. Doppler effect. And then here you have the redshift, which is equal to V over C. This is an approximation, to be completely honest, that only works for the open 25C. Then you also have this, which is the actual value, and this, which is a derivation of that. These are related. This is an approximation. I should have made it an approximation, but I'm sorry for that. And well, yeah, C is the common notation that we use for redshift. And then the rest are just, well, v is the recession speed, c is the speed of light, which has a constant value. Delta lambda is the change of wavelength, so lambda emitted minus lambda minus real lambda. I would rather say I would change emitted for received for the one we see. So there's a mistake here. Apologies for that. R is the cosmic scale factor, and R naught is the cosmic scale factor at a certain moment, which will be lower than R, which is the cosmic scale factor now. Okay, so cosmological principle, and we're getting close to the end of this. So the universe is homogeneous and isotropic, which means homogeneous means any section of the universe is similar to the other. It doesn't mean it's the same, but it is similar. We looked at the grand scale of things. And isotropic universe, what we see looking in any direction is the same as others see looking from any direction. So, in other words, what this means, the thing I want you to take out from this definition is that the universe has no borders or no center. So, which is a really important thing to note. There's no such thing as the center of the universe. There's no such thing as the borders of the universe. It's the same all around. Which makes it weird to think what happens at the end of the universe, but those are questions that I haven't even bothered to ask myself, and you probably shouldn't be asking either. I don't know what happens at the when you get farther away. I assume it will just look the same in all it looks the same in all directions. So there's really no such thing as the border of the universe. There's a border to the observable universe, but so critical density. It's the theoretical density that would stop the expansion of the universe after an infinite time. Okay? So it's given by this formula. I will go over derivation in a second, once we're done with the revision session, but because it is a thing they can ask in the exam. So three things can happen. The universe can be closed. So if the density of the universe is greater than the critical density, the universe will stop expanding and it will contract at one point, which we call the big crunch, and is all going to happen. I'm sorry. Plane universe, is that how it's called? Flat universe, maybe. If the density is equal to the critical density, it's flat universe, right? Whatever. The speed of expansion will become 0. And open universe, if the critical density is smaller than the actual density of the universe will expand indefinitely. So this is the different curves. High density, as you see, it basically comes back here. And then we have critical density, which kind of just means it kind of tends to a constant over time. And low density, it kind of keeps expanding indefinitely. And we are actually here, accelerating. But I'll get to that in a second. So, dark energy. We've observed that that density gets really close to the critical density. But the data seems to indicate that the universe is expanding, and it's expanding faster every time. And from these observations, the concept of dark energy was born. So there must be something causing this expansion. We'll come back to dark energy in like 2 slides. Black matter. It's matter that we think is there, but has never been observed due to it not absorbing or emitting radiation. There are several theories to explain dark matter. These are the ones you have to know. Matros is basically just proven to be impossible. So matros are massive compact halo objects, which are objects of high mass, planets, stars, and black holes that do not emit enough radiation to be detected. But there's not enough of them to actually account for the amount of mass that black matter composes, or that black matter makes up in a galaxy. And WIMPs are weak interactive massive particles. They're small particles, of which there are a lot of, but they're hard to detect. There's another theory that I learned about recently called SIMPs, strong interactive massive particles, which is basically protons and neutrons making up all this unaccounted for mass. But WIMPs is actually the most believed explanation, or the most likely explanation at this point. And okay, this looks hideous, but this is supposed to be over there. But okay, so here's the rotation curve for galaxies. This is actually what we use to evidence, or to this is how we came up with the idea of black matter. There's something to be something needs to explain this, right? So according to all our knowledge of physics, about observing the disk, we should see a velocity that decays with distance. But rather, what we see is a velocity that basically stays constant with distance. And that's weird. So there's got to be mass somewhere that is causing this to happen. And so we said, okay, there's mass, we can't see it, it's called black matter, and it's around the galaxy in a thing called a halo. And that's how black matter was born. It has never been observed. It is a concept proposed, so dark energy, as I said, I'd come back to it. So it's a concept proposed to explain the expansion of the universe. It exerts a negative pressure in opposite direction to any possible contraction. It's hypothetical, but it's believed to be homogeneous, so it's present in all space at really low densities. It could constitute around 68% of the mass energy content of the universe. As some of you may know, the mass and energy are related by Einstein's equation E equals mc squared. So basically, mass and energy are sort of the same thing. Essentially, that's what it's trying to say. And so dark energy could account for 68% of the mass energy of the universe. I believe black matter would be another 20%, maybe. And then normal matter is around 10%, something like that. But anyway, most of it is dark energy. Then the second most abundant thing would be black matter. And then we'd have normal matter, which is the thing we've never like all of, well, yeah. So it's believed to be an intrinsic property of the universe. And it grows as the universe grows. So the bigger the universe, the more dark energy it has. But as I said, it's all hypothetical. We know nothing about it, and we've never observed it. So creation of heavy elements. There are several ways by which the elements of the periodic table are created, right? Because if you think about it, it all started with hydrogen atoms with single protons, and then we now have uranium-238 and all of that stuff. But where does it come from? Well, it comes from processes like this. There are several more. Kilonovas are another one. Supernovas actually look at neutron capture, but kilonovas, and there's a ton of processes that create elements. These are the two you look at, and these are high level, but they're really cool. So nucleosynthesis. It's the creation of heavier elements via fusion, right? So this is what happens in the core of a star. Due to the increase in temperature, particles have increased kinetic energy, which allows them to overcome the repulsive forces in the nucleus and fuse together. So yeah, essentially, temperature more temperature means more kinetic energy. More kinetic energy means more energy, and that allows the particles to overcome the repulsive Coulomb force present in the nucleus due to positive charges, and basically that allows for atoms to fuse together and form another atom, and this releases a tiny bit of energy, which is what basically prevents the star from collapsing inwards. Obviously, it's not one fusion per second; there's millions and millions of them every second, but they add up. So, depending on the mass of the star, one of three things can happen. If the mass is lower than 4 solar masses, this means solar. A red giant. Carbon and oxygen are generated in the nucleus, and helium is formed in the outer layers. You have to understand that I'm not talking main sequence stars here, because main sequence stars produce helium in the nucleus, and that's it. When they move outside of the main sequence, it's when they start producing these heavier elements. So red giants produce carbon and oxygen in the nucleus, and they have a temperature in the nucleus of around 10 to the 8 Kelvin. Between 4 and 8 solar masses, which are also red giants, neon and magnesium are formed in the nucleus, and carbon, oxygen, and helium are formed in the outer layers, which is 10 to the 9 Kelvin. So think of it like an onion, right? So at the core of the onion, you have neon and magnesium, and then as you start peeling away the onion, actually, well, you start from the outside, but no, it's supposed to be helium. I made a mistake when I was typing. It's supposed to be helium. And silicon and iron. So for mass greater than 8 solar masses, actually it could be nitrogen, but no. Silicon and iron are formed in the nucleus, and lighter elements are formed in the outer layers. So one thing I would like to point out: it's they only form up to iron. Can anyone tell me why only up to iron? Why not go to? I mean, I could check my notes here properly, but creative. I know you know this, for Christ's sake. Can anyone else try? I mean, I'll let creative answer if no one else wants to try. Yes, it does have to do with the max binding energy per nucleon, but like, what does that mean? As in, it has the greatest binding energy per nucleon. What does it mean when it comes to fusion?
So that the energy is too unstable.
No, it's no, it's the most stable element actually. Creative, do you want to answer it since?
Sure. Actually, oh no, it's typing. Anyway, I'll explain it. If no one else is gonna answer. So, yes, it has the maximum binding energy per nucleon, which means it's, yes, the most stable. So what that implies is, if you were to do nuclear fusion using iron to form heavier elements, that would require taking in energy, which is unfavorable. And so, like, if you think about it, the star is in balance from gravity pulling inwards and nuclear energy pushing outwards. But then if you have a nuclear process that takes in energy, that sort of ruins that whole balance and a star starts to die.
Yep, it's exactly that. So essentially, since it's a high binding energy, you can't fuse it into you can't fuse it into anything, but it doesn't release energy. You need to input energy into the system, and that means that you basically it can no longer create energy to push outwards gravity, so the star starts collapsing onto itself. Okay, so the next thing we'll be looking at is neutron capture, which is actually the last thing we'll be looking at as well. And since they don't have charge, neutrons can get closer to the nucleus and get captured by the nuclear forces present there. Via beta plus decay, it can decay into a proton and given rise to a new element. This can happen in one of two ways. It can happen via the S process, or it can happen via the R process, which is the S process is capture of thermal neutrons, and the R process is the capture of fast neutrons. That's supposed to be neutrons. I apologize again. Um, so, okay, we'll start by looking at the S process. The S process takes place in certain red giants over long periods of time, and by long I mean really long. I mean, take into account we're talking astronomical astrophysics here, so long periods are insanely long, and short periods are really long as well. What we call imminent in physics means it's going to in astrophysics it's going to happen in roughly maybe a million years or maybe more. With a relatively low neutron density and intermediate stellar temperatures. And so the capture of neutrons becomes less likely than beta decay. And so you get a neutron coming into a nucleus. So you basically increase, and then it decays. This is supposed to be the decay actually. You would get A plus 1 and C plus 0. So it decays, and so you get an element Y with one more proton and one more mass number. It releases an electron and a neutrino, antineutrino to make the reaction balance out of both sides, so that the charge is the same. And elements until bismuth 209 are created via this process. Don't ask me why it's up to bismuth 209. I assume it's because the process is really slow, and then at that point it becomes really unlikely to create anything greater than bismuth 209. But essentially, what's going on is an electron is coming into a nucleus, it's decaying into a proton, it's releasing an electron to keep the equation balanced, to keep conservation of charge, and that releases a neutrino and therefore an antineutrino, and you get another element that these can create elements that are heavier than iron, because it's not technically fusion. You're not technically inputting energy into the system. Our process. A great variety of elements can be formed via this process, including the most massive ones. It happens very quickly in supernovas. So this one is one that occurs in supernovas, which have a very high density of neutrons and very high temperatures. At that point, neutron becomes more likely than beta decay. So essentially what happens here is that there's a ton of neutrons flying around, and there's elements, and those neutrons kind of go into the nucleus and decay eventually. But And so you get elements, and then more neutrons come, you get more elements. And so beta decay leads to transmutation to other elements. And those beta decays lead to neutrinos being created, which means that you see a ton of neutrinos being created in supernovas. Is this clear? Is this last part clear? Okay, I'm gonna assume it is. Well, that's it for the revision session. Do you guys have any questions? I will go over some exercises now, but I won't be filming them.